Hi, in this video we're going to work on maxima minima and modeling problems with differentiation. Now let's remember some basics. First of all, differentiation is about measuring rate of change. Now let me explain what I mean with this term or phrase. So let's think about two cars. Under normal circumstances, these two cars can travel 60 kilometers of this distance and complete it. But if we consider how long it will take for these cars to finish it, right? We know that one of the cars will be faster than the other. And now we're talking about velocity, right? So both cars completed the track, but one of them finished earlier than the other. So actually, we're talking about rate of change here. One of the cars changed its displacement faster than the other. And when it comes to how fast these cars are getting faster, right? Now, let's consider this example. Suppose that this car starts from here, all right? So when Ferrari starts, it hurries up, so it goes really fast, which means in terms of velocity, if we have a graph, its velocity goes really high as a function, and the change in velocity, all right, let's say this graph, okay, it is an increasing function, all right? And let's consider now, just because Ferrari caught up with the Mini, right? It slows down, but still faster than Mini. It slows down because it knows that it's going to win, right? Now, the velocity could decrease or could go like this, or it could even go down. It doesn't matter. It's still faster than Mini, right? So it can complete the race first. But for this graph, we will just jump down to negative, right? Now, if this is the velocity versus time graph, this is the acceleration versus time. Now, when your velocity slows down increasing, or it does not increase at all, or it's decreasing, then you go to negative values of acceleration. So this is the rate of change of velocity that we call acceleration. So that's how we measure rate of change. It's all related to differentiation. And I think from IGCSE you remember that we calculate velocity from the derivative of displacement versus time, and we calculate acceleration from the derivative of velocity versus time. So these are all calculations of rate of change. How fast is a car compared to the other velocity? How fast is a car going faster or slower? Acceleration, right? Now, certainly it is very important to figure out the maximum and minimum values when it comes to measuring rate of change. It has many applications. For example, take the Ferrari here, right? Now, what is the minimum weight that a Ferrari can be so that it can reach its maximum limit in velocity, for example? Or what is the minimum capacity of its gas tank so it's going to keep its weight in an optimum level, but so that the weight will not slow it down, but at the same time it will go as many kilometers as possible? Or in economy, consider a business. It has costs, it has revenue, it has profit. So how can this company keep the costs in a minimum while maximizing its revenue? Or what is the optimum way of increasing the company's size to maximize the revenue and keep the cost increase in a minimum? And these are all about modeling and functions and differentiation. Now let's see some examples. Given that the volume of an expanding sphere is related to its radius, by the formula, we know that. Find the rate of change of volume with respect to radius at the instant when the radius is 5 centimeters. Now, this is the part I kept mentioning while teaching differentiation. We have to state the variables while differentiating. So now I have to write the derivative of volume by radius. Now, we don't have any other variable in this formula, but just r. But in case we have more than one variable, we have to define which variable we're using, right? So the derivative of volume with respect to radius is, now we have the 4/3 here, and pi times, we are going to multiply by 3, and it's going to be r squared. We have to take away 1 from the power. So if we use simplification here, we're going to have 4 pi r squared. Now this is the formula of the surface area of a sphere. A coincidence? Worth checking. Now let's go on. The radius is given to be 5, so let's calculate the rate of change while r is 5. So all I have to do is to substitute 5 here into this formula and get this 25 times 4, it's 100 pi as the rate of change when r is 5. Now the question didn't mention whether we have to round this, but to figure out easily what this value is all about, it's around 314, let's say up to 3 significant figures. Now what is this 314? This is the most important part. We're trying to find the rate of change of volume with respect to radius. So we have to now interpret our finding. What we have found is that the rate of change of volume with respect to radius is 314 centimeter cubed per centimeter. Now this sounds like, we increase the volume 314 centimeter cube every single time we increase the radius 1 centimeter. Well, this is not the case, because if you calculate, for example, the rate of change when radius is 6, we get 452 centimeter cubed as a rate of change. So obviously it is not that, and actually we cannot consider this increase as linear because of the square here, right? We're taking the square of the radius, so obviously this is not a linear increase. So it is not about that. It is just a comparison here. But the rate of change itself is a function too. So it is changing as well. As you can see, the radius is 6. The rate of change is 452. So for any given radius, we are going to find a different rate of change, because rate of change itself is a function too. So we just calculated the rate of change of volume when the radius is 5. That's it. So within the scope of pure maths 2, we only need to know this much. Another example. So please pause the video now to read the whole question. Now this is where the modeling starts. You have to draw a cuboid and then start labeling the dimensions. So we know that the two ends are squares, so it's x and x. Let's consider the length of this cuboid to be y. So first, let's write the volume. Volume is the area of the cross section multiplied by the length. So it's going to be x squared y. Now my problem is I need the volume in one variable. As you can see, it is given as in terms of x only. So I have to figure out y in terms of x so that I can substitute it here. So I know that this cuboid is made up of 54 meters squared of sheet of metal. So this is the surface area of the tank. Okay, so let me calculate the surface area of this tank. I'm going to go like I have two ends which are squares, so it's going to be 2 times x squared because there are two squares, plus, now I know that the rectangles are each xy, right? X times y here, and I have 3 of them, not 4, because it says the tank has a horizontal base and no top. So the top is open, so there is no rectangle here. So it's 2x squared plus 3xy. Now this is given to be 54 meters squared. Now let's try to leave y alone. So it's going to be 54 minus 2x squared equals 3xy. And if I divide both sides by 3x, I'm going to get y to be 54 minus 2x squared over 3x. So this is the expression I'm going to substitute for y in here. So let's do that. So b equals x squared times 54 minus 2x squared over 3x. And I can simplify one of the x's with this one here. And if I distribute the remaining x over the brackets, I will have 54x minus 2x cubed over 3. Now I'm one step far to the solution. I can think of these as separate fractions, right? So it's 54x over 3, which will be 18x minus 2/3 of x cubed. So it's shown. Now in part B it says, given that x can vary, use differentiation to find the maximum and minimum value of v. Now the only thing that restricts us is the area. But once we are stuck with this, and this is what we do actually, we are stuck with the area, the volume could be expressed with this equation, right? Now, if I differentiate this, I can calculate the maximum and minimum values of the volume of the tank. So let's do so. So let's write the derivative of volume with respect to x. It's going to be 18 minus 2/3 times 3 times x squared. So if I simplify these, I'm going to get the derivative to be 18 minus 2x squared. Now if I equate it to 0, I can find the x values which will give the volume to be maximum and minimum. So x is plus and minus 3, and obviously I'll choose x to be 3 because it is a length, so it must be positive. So when I substitute this value here for volume, I get 36 centimeter cubed, and this is either the maximum or minimum value of the volume. For part C, we have to go through the second derivative of volume. And when we substitute x equals 3 into the second derivative, if we find negative value, then the volume is maximum. If we find a positive value, then the volume is minimum. So the second derivative of this volume is minus 4x here. And when you substitute x here, x is 3, so it's going to be minus 4 times 3, which is minus 12. This is less than 0. This implies that the volume, which we find to be 36 centimeter cubed, is a maximum value. So the maximum minimum problems are not any different than what we had in IGCSE, but it is a little bit modeling involved, so you have to figure out what the story is all about, and it's best if you try to visualize what is given so that you can find your way. But of course, as always, practice makes perfect, so you have to try the questions on your own. Thanks for watching.